Hello everyone, I'm Erdem Bıyık from Stanford University. Today I'm going to talk about an open source Python library, APREL, that we recently released. This library provides useful tools for active preference-based reward learning. It's a joint work with Aditi, Talati, and Dorsa, Sadigh. Let me start with a problem definition. Let's say we have a user who wants a robot to perform a task. The user has an internal reward function that he wants the robot to optimize. However, the robot doesn't know this reward function. To mathematically formulate the problem, let me use this example. The robot is tasked with reaching the notebook on the table while avoiding the obstacle. The psi here shows an example trajectory. We assume there is a known function phi that maps each trajectory to a set of features. For example, in this task, the features can be final distance to the goal, how close the robot gets to the obstacle, its average speed, etc. And the robot gets a reward that's some function of these features parameterized by w. Here, w is the only unknown variable. The goal in reward learning is to learn this w. This is a very common problem, and preference-based approaches, which I'll explain in a bit, provide effective solutions. But unfortunately, there is no unified library or benchmark for preference-based reward learning. Everyone builds their own code base for the specific project they are working on. This is not great for reproducibility or efficiency of comparing different approaches. Hence, we decided to develop a unifying Python library for active preference-based reward learning. We call this library APREL. I'm now going to talk about the components and the structure of this library. So, in our problem, we have a human and a robot, and the human provides some data to the robot. For example, it can give expert demonstrations, as in this video. These demonstrations are passively collected data, and they will help the robot better identify the unknown reward parameters W. So we have a human providing data to a robot. The robot will then adopt a human model for the collected data. For example, in Bayesian inverse reinforcement learning, we assume the probability of an expert demonstration is proportional to the exponential of its reward. Our library APREL allows designers to customize the human model they want to adopt. Having a model, the robot will then use the passive data to build a belief distribution over the reward parameters W. We can further refine this distribution by querying the user with some questions. This is the idea in active preference-based reward learning. Now, I want to give some examples of such questions. One example is pairwise comparisons. The robot shows two trajectories to the user, and then we ask the user whether they prefer trajectory A or trajectory B. Again, all we need is a response model for the human. For example, we can use the softmax model where the selection probabilities are again proportional to the exponential of the rewards. In APREL, the designers are not restricted to the pairwise comparison queries. For example, another query type that's readily implemented is weak comparisons, where the user is given a chance to say they are indifferent between two options. Again, all APREL needs is a response model. Also, queries do not have to consist of two trajectories. Another query type is rankings, where the user ranks a given set of trajectories, and APREL will only need a model for each possible response. For example, loose choice axiom extends the softmax model to these ranking queries. But overall, the point is that the designers are not restricted to the query types that we implemented. They can be creative and come up with new types. After the robot queries the user with a question, the user is going to respond to the query. But one thing is very important to note in active preference-based learning. While the robot has no control over the passive data, it can actually decide what query it wants to ask the user. Therefore, it can optimize the query using some acquisition function, which is the objective of the optimization, and possibly the dynamics of the task. The feature function, which maps trajectories to the features, is also known. APREL is compatible with OpenAI Gym, so any task that follows the environment structure of OpenAI Gym can be used in APREL. I also want to talk about the optimization options APREL provides. First of all, it readily includes several different acquisition functions. These are volume removal, where the goal is to remove the maximum volume from the belief distribution, disagreement, which queries the user with trajectories that are likely but dissimilar, mutual information, which tries to maximize the information that will be gained from the user's response, regret, which queries the trajectories that are likely but would incur high regret with respect to each other, and Thompson sampling, which uses samples from the belief distribution to generate the query. Of course, the choice of acquisition function depends on query type, the task, and the overall objective. So the designers are not limited to these acquisition functions. They can easily add their own functions to the library. In addition to the acquisition functions, we can also change the number of queries we want to generate at each active learning iteration. In other words, we can also do batch active learning. This is useful when query optimization is costly or when data collection can be parallelized. For this, APREL includes heuristic methods like greedy batch generation, medoids, and boundary medoids methods, or more founded techniques like successive elimination and deterministical point process-based batch generation. At the end, our optimizer generates one or more queries with an acquisition function we selected. The user responds to these queries, and we update our belief distribution about the unknown reward parameter W. This process repeats multiple times until the distribution is confident enough about W. Finally, we assess the quality of the learned W or the posterior distribution. I want to emphasize again that almost all blocks in this diagram are customizable in APREL. For example, any OpenAI Gym-compatible environment can be plugged in, and the designers implement their own feature function of the task. Or new acquisition functions for query optimization can be implemented and experimented, as well as the optimization method. In this talk, I only mentioned expert demonstrations for the passive data, but other forms of data can also be implemented. This would of course inform the optimization method and the acquisition function, as well as the human model. One may also want to use different priors or belief update methods. APREL readily includes Metropolis Hastings sampling-based method, which is the most commonly used technique in preference-based reward learning, but other approaches can be implemented. Finally, assessment depends on the overall objective. For example, when the goal is to learn W perfectly, a common assessment measure is cosine similarity. However, other metrics, such as regret, can also be implemented. For the rest of the talk, I want to go over a simple example of how APREL is used. For this, I will show you a full Python code where we use APREL. First of all, we are going to import it along with the other libraries. Then we are going to create an OpenAI Gym environment. This is the environment in which we want to learn the reward function. Let's say we use one of the default gym environments, mountain car. In the code, we will just create this environment as usual. What APREL requires is a features function that accompanies the environment. So we will implement a function. Simply, it's a function that takes a trajectory, a sequence of state action pairs, and returns the features associated with this trajectory. For example, in this case, we let the features to be the minimum position, maximum position, and the mean of the speed of the mountain car. We will then wrap this function with the OpenAI Gym environment. Next, we initialize an optimizer for our queries. For this example, we will use an optimizer that simply loops over a pre-generated set of trajectories. So the first line here generates this set of trajectories, and the last line defines the optimizer. APREL allows both real humans and simulated humans to respond to the queries. Let's say a real human is going to respond. As I said, we will also need a model of how human responds to the queries. Let's use softmax model that I described earlier. In this specific model, we will model the reward function as a linear function of the features, so the unknown variable W is the weight of the reward function. Following most of the existing work, we will use a sampling-based belief. That is, we will keep all user responses in a database and sample from the true posterior when needed. Finally, let's say we want to query the user with pairwise comparisons. For this, we will create a dummy pairwise comparison query. The optimizer will then return a query of the same type, but with the optimized trajectories in it. So we are now ready to do the active learning loop. In APREL, this is actually a very simple loop. Iteratively, we first have the optimizer optimize a query, then the user responds to this query, and we update our belief about the reward parameters based on their response. Here, I'm showing a non-batch version of the optimization, but the batch versions are also similar. We would just add an argument to the optimizer so that it will return a batch of queries. At the end, we report the learned parameters. Okay, we are now done with the code. When we run it, it will query us with multiple pairwise comparison questions. Here is one of them. The original goal in mountain car is to reach the yellow flag. So let's say we prefer the left one because it pushes forward slightly more than the right one. We will respond to several such queries. Let me skip that process and just show you the end result after 10 queries. Remember, our feature function had 3 features: minimum position, maximum position, and mean speed. APREL returns this when the active learning loop is complete. As you can see, the weight for the first feature is negative and the other 2 are positive. This means it wants to minimize the minimum position while maximizing the maximum position and the mean speed. We took this learned reward and trained the policy using soft actor critic with it. This is what we got. It's a policy that successfully achieves the task. But you'll see that the car makes sure to hit the left wall before passing the yellow flag. This is because the reward function encourages it to also minimize the minimum position. So, by designing the features in this way, we gave it another objective, which might be unnecessary. And this informs us about one of the future research directions. In APREL, or in preference-based reward learning in general, future design is crucial. Instead of relying on the designer effort to have these features, it would be very beneficial if future design was automated by, for example, using neural models. Secondly, APREL performs Bayesian learning. It keeps a belief distribution over the unknown reward parameters. This might be computationally too expensive when the parameter space is very high dimensional. So, gradient-based learning methods would be a valuable extension. If you are interested in using APREL in your projects, you can scan this QR code to reach the library, its documentation, and examples. We hope it will enable the community to more efficiently develop and experiment new reward learning methods. Thank you.